Calculus of a Single Variable, 6th edition. Chapter 8, Infinite Series. Review exercises. Number 81. Show that the function defined by the series is a solution of the differential equation. Pause the video now if you'd like to give it a try. So we want to show that the series given by y equals the infinite sum starting from n equals 0 to infinity of negative 1 to the n power x to the 2n power over 4 to the nth power n factorial squared is a solution to the differential equation x squared y double prime plus xy prime plus x squared y is equal to 0. This is going to require us to differentiate the power series twice. Once we do that, then we can substitute this into the differential equation and verify the solution is correct. So first, y prime. We want to differentiate this with respect to x, so everything in the series expression that's not in terms of x will be treated like a constant. So only what I have highlighted in yellow is what got differentiated by the power rule of differentiation. Next, we notice that this series is the same as if we had started it from n equals 1, because at n equals 0, the first term would be 0. Then what we can do is a little trick we call re-indexing by changing the variable n by shifting it over 1. So all the variables n get shifted over to n plus 1, and so we adjust all of the terms accordingly. Now n starts at 0. Next, we differentiate a second time with respect to x, and we get a new coefficient n 2n minus 1, and then x is raised to the 2n minus 2 power. Everything else is the same. We notice that this would be the same series as if we started at n equals 1. And if we look closely, we can then take the same steps that we did in the y prime to re-index the series to let it start again at 0. We do this by letting n go to n plus 1 in the formula. So now that we have expressions for y prime and y double prime, we can put them to use and substitute them into the differential equation. We're going to have to multiply y prime by x and y double prime by x squared, which is only going to bump their powers up in terms of x. So let me write out the differential equation that we have to satisfy. X squared y double prime plus xy prime plus x squared y equals 0. And now I'm going to substitute in the power series that we found by differentiating, noticing that the x's have been boosted by the appropriate powers of x. I started here with the series for x squared y, and now I'm inputting the series for xy prime. X squared y double prime. And lastly, I'll input the middle term, the series for xy prime. So I just simply wrote these series out of order, but you'll see what I'm doing in a moment. All of these need to be equal to 0 when summed up. So we notice that these two series that I've just checked off are both in terms of x to the 2n plus 2 power. So I can combine those two series by adding them together and writing them as a single series. Factoring out a negative 1 to the nth power x to the 2n plus 2 all over 4 to the nth power n factorial squared, I can write out the term that would be left after combining those two series, and then writing the leftover middle series on the end there in red. Now, doing a little bit of algebra and combining some of those things in the brackets, we can rewrite what's in there, clean it up a little bit. We'll finish with that in just a moment. And noticing that the series in red here would be the same as if we started it at n equals 1. So I'm just going to rewrite it here starting with n equals 1, which will allow me to then re-index this. The purpose of re-indexing it is that it's going to allow me to boost the powers of x so that the powers of x in both series match. In fact, now I have x to the 2n plus 2 power in both series, so now I'll be able to combine all of the series together. Doing a little bit more algebra in the term that we added previously, and now combining everything, we're going to see why the left-hand side in fact must equal 0, proving that the differential equation does in fact equal 0 when we substitute it in our power series solution. So the whole purpose of manipulating these series and trying to re-index them is to try to match powers of x in all of the series that you're trying to add together and have them start at the same n value starting at n equals 0 here. And finally, we arrive at the proof. Now, we have verified that the series that they provided us with, this very elaborate looking series, is a solution to the differential equation x squared y double prime plus xy prime plus x squared y equals 0. But where did this solution come from? I mean, it is so elaborate, it doesn't seem like someone could guess this solution. So how was this solution obtained? That's the next part of our video. So, we're going to solve the differential equation that was given to us using a power series method. A method that was developed by the mathematicians Frobenius and Fuchs. So we first start off by assuming that y is going to be equal to some solution of a power series form, with Cn being the coefficients. We then go ahead and differentiate y with respect to x as we did when we verified the solution, although here now we're just writing it in general in terms of the coefficients c, and we're re-indexing as we did in the proof. Finding the second derivative with respect to x, rewriting it with n starting at 1 because it would be equivalent, and in this case we could start it at n equals 2 and it would still be equivalent. Then we can take one of these series or all of them and re-index them as well by changing their n values so that we could see which one of the series would best help us match with the other series when we add them together. Alright, so just re-indexing here, playing around with the series, making sure that all n's are adjusted accordingly. Alright, and now that we have differentiated our general power series, we're going to consider the differential equation that we were looking at earlier. And we're going to now also adjust for the fact that some of these power series are being multiplied by x squared or x. So that's just going to boost their powers of x appropriately. So both the y and y double prime will have their powers of x boosted by 2, and y prime will have its powers boosted for x in just 1 degree. So again, like I did before, I'm going to start off with x squared y term. And writing in the rest here, what I'm trying to do is, as best as possible, match the series that have the same powers of x. So the first two series that I have written there, I could combine them together because they both start at n equals 0, and are in terms of x to the n plus 2 power, so I can combine their coefficients together. And all I'm going to do is rewrite the last term, the last series there, and play around with it so that I can get its power of x to be 1 power greater. So what I'm going to do is I'm going to first sort of write out what the first term of that series is, and then write out the rest of the series starting at n equals 1. From there I can then re-index that remaining series, and by doing so I will have a power of x that is related to the first power of x that we were dealing with in this series. In other words, I can combine all those infinite series together now, all in terms of x to the n plus 2 power. So, combining all the coefficients carefully, all in terms of powers of x to the n plus 2 power, plus that term that we pulled out of the last series. If this equation is equal to 0, that implies that the coefficient c1 must be equal to 0, and the coefficients in the summation there must also be 0. And I simplified that there a little bit, and solving that particular equation, we get a recursive formula for the coefficients of our power series, and this is how we're going to develop the general formula. So now we're going to let n equal 0 and let this formula generate a couple of terms to see what they look like, develop a general pattern. So when n equals 0, we get c2 is equal to negative c0 over 2 squared. c3 is going to be equal to negative c1 over 3 squared, but since c1 is equal to 0, that's going to be 0. And we're going to see all of the n equals odd numbered terms are going to be equal to 0. All the even numbered terms are going to be able to be written in terms of the coefficient c0. And as we increase the number n, we see that the denominator is going to be equal to certain powers of 2 times factorial squared. As we just generate a few more terms, it'll make the pattern a little more clear. So we'll go out to n equals 4, which will give us the term c6 is equal to negative c4 over 6 squared, and then we just replace some of those variables. Substitution. And finally, we can write out a general term. That last term should have a 2 cubed and then squared. Alright, so in general, the even terms will have an alternating series of negative positive 1, so we have negative 1 to the nth power multiplied by the coefficient c0 over 2 to the 2n power times n factorial squared, or in the in the denominator we could write that as 4 to the nth power instead of 2 to the 2nth power. All the odd coefficients would be 0, so writing out our final solution, y is equal to the infinite series, starting from n equals 0 to infinity, of negative 1 to the nth power c sub 0 x to the 2n power over 4 to the n factorial squared, where the coefficient c sub 0 would be determined by some initial conditions given by the differential equation. And so this represents the general solution. And the one that we verified earlier was with c sub 0 equal to 1. I hope you enjoyed this video. Please stay tuned, hit the like and subscribe button for more videos.